All right, we're going to be talking about composite functions today, and what composite functions are is really taking one function and putting it in another to be evaluated. And this gets a little bit tricky, especially with notation. So the idea here is you're given two functions, f and g. The composition is denoted as, I always looked at it as that fog, f composed with g, that's a circle. Okay, f composed with g is defined by the following. Here's the notation. And here's how we write it. It's f of g of x. That's how we say that, f of g of x. And this is what we mean. One function inside of another function to be evaluated. Now, composition functions, when you get into calculus, when we take derivatives, we use what's called the chain rule to help us with these composition functions. So what we're going to do today is just evaluate functions where we're given x and when we're not given x, and we have to simplify by plugging one function into another. So that's the big idea here. And one thing you got to notice when we talk about inverses later on, if f of g of x is equal to g of f of x and they both equal x, the functions are inverses. So you got to be really careful. F of g of x and g of f of x, they're not necessarily the same. Okay? They're not like the commutative property where you flip and you're going to get the same result. So you got to be very careful of that. So in our first example, let's let f of x be 2x squared minus 3, and g of x is going to be 4. Find each of the following. So there's four things we're going to be looking at. In part A, we're looking at f composed with g of 1. So what this tells us, we're looking for f of g of 1, which is written here. So here's the idea. We have this function f, and we've got to input g of 1. So the first thing I need to know is what g of 1 is, which I've shown you here. G of 1 is just 4 times 1. You're plugging 1 into your function g. So now that I know g of 1 is 4, that 4 replaces the g of 1. And now 4 goes into your function f. So f is this function here, 2x squared minus 3. So you have 2 times the quantity 4 squared minus 3, which is 2 times 16 minus 3, which becomes 29 when you simplify. In part B, we've switched g and f around, and we're still using the number 1. Now here's what I want you to think, that these are automatically equal. This is not commutative, so you don't just switch and say, well, it's the same result. You're going to see here that they're not the same result. So when we have g of f of 1, we're looking to take g of f of 1. So like before, we need to know what f of 1 is. So if we plug 1 in for x, you get 2 minus 3, which is negative 1. So negative 1 is going to replace f of 1. So g of negative 1 becomes 4 times negative 1, which is just negative 4. Obviously, you can see these two are not equal, so we can't say the compositions are commutative in any way. In part C and D, we're going to actually compose the functions with themselves. So in C, we've changed our x value to negative 2. And so we're taking f of f composed with f. So what you're looking for is f of negative 2, and then that's going to be plugged into your function f. So step number 1, find f of negative 2. 2 times the quantity negative 2 squared minus 3 becomes 2 times 4 minus 3, which is 5. So now that you know what f of negative 2 is, it's 5, you're going to replace the f of negative 2 with 5, and now 5 gets plugged into the same function f. So you plug 5 in and simplify, and we get 47. In part D, g composed with g of negative 1. So first, we've got to find g of negative 1. G of negative 1 here is 4 times negative 1, which is negative 4. And so negative 4 is going into function g. So 4 times negative 4 is negative 16. And that's g composed with g. Could we be quiet in the back? I'm trying to record this video. Zip it. I'm not stopping either, sorry. I'm covering Mr. Mungai. Now, in this example, we've got, again, two functions. F of x equals x squared plus 3x minus 1. And g of x is going to be 2x plus 3. And we're going to find two examples. So we have f of g of x. The important thing to realize here now is we don't have an x value. So what's going to happen is we're going to have an expression. we're not going to have a numerical answer as we did in the last example. So f composed with g. What that means is f of g of x. So you can see that g of x in red has to be plugged into f. Well, in the next line down, don't we know what g of x is? We know g of x is equal to 2x plus 3. So we replace g of x with 2x plus 3. Now, 2x plus 3 gets plugged into f. So that means 2x plus 3 goes into x in f of x. So we're going to have 2x plus 3 squared plus 3 times 2x plus 3, that quantity, minus 1. So once we plug in our new x, our new argument, 2x plus 3, you have to simplify. We have to expand 2x plus 3 squared, and we get 4x squared plus 12x plus 9 plus 6x plus 9. This part here, that's the distributive property with the 3, and then there's the minus 1. And then finally, make sure you combine like terms. So we end up with 4x squared plus 18x plus 17. Now, since this is a polynomial, the domain is all real numbers. Okay? So just be aware of that. If they ask you for domain, look at the function here. It's a polynomial. Domain is all real numbers. In part B, we're going to go g composed with f. We're going to switch g and f around. Again, this is not commutative, so don't just put the answer that you got in the previous example. So we want g composed with f, and that means we want g of f of x. So here's our two functions. I just relisted them here for you. So g of f of x. We know that f of x is equal to x squared plus 3x minus 1. So just replace the f of x with what you know that function to be. We've done that in this step. And now you plug in, your new argument for g is not x anymore. It's this argument, x squared plus 3x minus 1. So 2 times x plus 3. Our new x is this. So we have 2 times the quantity x squared plus 3x minus 1. We distribute the 2 and then combine like terms. So we've done that here, distribute the 2 and combine our like terms. The only like terms that we have here are the 2 and the minus 2 and the plus 3, which gives us 1 there. Again, this is a polynomial, so the domain would be all real numbers. Now, here's one that you got to be real tricky of our last one. This is a square root function. So if I were to give you an x value, you got to make sure your x is in the domain of both your functions. So f of x here is the square root of x plus 1, and g of x equals 3x. So let's look at f composed with g, which is the following, f of g of x. Again, it's the same thing. You rewrite your composition, you know what g of x is. G of x is 3x, so replace it. So now 3 of x is your new argument that's going into f. 3x is going to replace that x right there in f. And that's what we do. The square root of 3x plus 1. These are not like terms. The domain here, again, your radicand has to be greater than or equal to 0, so we get negative 1/3 to infinity is the domain. Part B, again, g composed with f of x. You want g of f of x, so similar idea. You have f of x, you know what that is. You're going to replace f of x with what it's equal. In this case, the square root of x plus 1. And the square root of x plus 1 is going into g. So you have now 3 times the square root of x plus 1, which is just 3 times root of x plus 1. Again, making sure you know what the domain is. X has to be greater than or equal to negative 1, and there's the domain here. So that's compositional functions. You plug one function into another to be evaluated. That's the idea. Composition functions are not commutative. We've shown every example here. Just because you switch the f and g around doesn't mean you're going to get the same result. So be very careful with that. Again, if you need to, use different colors so you know which function's going inside of which. If you have any questions or comments, you can just email me or type them below. My email is nicholas.bennett@dc.gov. Thanks.